Hi, my name is Marko Vukasinovic, and this is my Physics 2012 Lab 3 on circuits. The purpose of this lab is to use energy conservation, also known as the loop rule, and current conservation, which is charge conservation and the definition of steady state, to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential differences in the circuits, and finally to examine the behavior of ohmic resistors and capacitors. Moving on to some key physics principles and concepts used in this lab. The loop rule states that the sum of potential differences in any closed loop in a circuit is zero, which you can see here below in this diagram. The current conservation refers to the principle that current flowing into a junction must equal the current flowing out. As seen here to the right, it shows a fork in the circuit, and the current conservation principle means that current entering this fork must equal the current exiting it. And both these ideas were developed by Kirchhoff. Electrical resistance is the measure of how much material opposes the flow of electric current using Ohm's law, as shown here to the right. And this formula will be used in this lab, V equals IR, and derivations of this formula as shown. Capacitance is an object's ability to store electric charge, and the formula for that is C equals Q over V, where Q is charge and V is the voltage across the capacitor. And finally, a capacitor consists of two conductive plates separated by an insulator, creating an electric field between them, and the formula for that is C equals epsilon naught, which is the electrostatic constant, times the area divided by the distance between the plates. Now, for a quick preview of the findings, the current in the series circuit is 0.02 amperes. The sum of potential differences is 0, which makes sense as for the loop rule. And as resistance increases, the magnitude of current decreases. And finally, the larger the resistor, the longer it takes the capacitor to gain or lose charge. For part 1 of the experiment, the system was the circuit as shown here to the right, and the surroundings was everything outside of the circuit that could possibly interfere with the experiment. But in this case, since the experiment was virtual, this would really be nothing. The initial conditions here are two 1.5 volt batteries and a 47 ohm and 100 ohm resistor in series, and then two ammeters across from each other as shown. In this experiment, I found that both the expected and experimental current were 0.02 amperes. For the change in voltage, I measured this value for each section of the circuit, and it's worth noting that when you add up each change in voltage, the net change is 0 volts, which should be expected. Then for resistance calculations, I used the formula V equals IR, and I found that the resistance of the 47 ohm resistor was 48 ohms, and the resistance of the 100 ohm resistor was 102 ohms, while the resistance of the wire and the ammeter were both 0 ohms. So there is a slight difference in the expected versus the experimental values here, because the 47 ohms resistor should be 47 ohms, but it was 48, and same with the 100 ohm resistor. And the source of error here is likely a software rounding error or imprecise ammeter reading. For part 2 of the experiment, the system is the RC circuit, and once again the surroundings is everything outside of the circuit, and the initial conditions are a 9 volt battery, 10 and 20 ohm light bulbs, and a 0.2F capacitor. I found that the charging and discharging for each bulb took roughly the same amount of time, and the relationship between this time and the resistance of the bulbs is directly proportional. Next, I plotted my findings as shown to the right, and I found that my experimental RC was 5.8 seconds, while the expected RC was 6 seconds, and both these values were pretty similar, which should be expected because the experiment was simulated and there wasn't too much room for error. However, the only notable source of error here was an error in time recordings. Moving on to what-if questions. If this experiment was done in real life and a real ammeter was used instead of the simulated ammeter, there would be a difference because in reality, ammeters do have a resistance, and when compared to the simulated ammeter with zero resistance, this would result in a lesser current due to a greater resistance running through the circuit. And finally, if this experiment was done in real life and a real battery was used to charge a real capacitor with no resistor in the circuit, there would once again be a difference in resistance of the real life wire as opposed to the simulated wire. The real life wire would have some resistance compared to the zero resistance wire in the simulation, and although this wouldn't make a huge difference, it would take the capacitor a little longer to charge.